Right. Once again, good afternoon to you all. Probably you remember that in the beginning of this module, we discussed about the open channel flow. Then we started the sediment transport chapter. So in the last class, we started to discuss about the groundwater flow. This groundwater flow has two sections. So the first section was about an introduction to the groundwater flow and the development of three-dimensional groundwater flow equation. So we finished that part during the last class. So today I am starting the second part of this groundwater section, that is the movement of groundwater and application of pumping test. Right. Right. So I will quickly go through what we did during the first class. There we discuss about the groundwater flow in general, right? So we started with a brief introduction to the groundwater aquifers. First, we discuss different kind of geological formations like the aquifer, aquitard, then the aquifluge, some impermeable layers, right? So these are different kind of geological formations. Then we discuss in detail about the aquifers. Aquifers, there are confined and unconfined aquifers. Then also sometimes local purge aquifers can be seen, right? So that the governing equation and the variation of the hydraulic head in these aquifers are different. Then we discuss about the aquifer properties. What kind of aquifer properties did we discuss? Can someone remind me? You can hear me, right? Can I make sure that you can hear me or not? I need one of you to please speak. Can you hear me?
Yes, sir.
Yes, sir.
Right. Okay. Then can you tell me what are the different aquifer properties we discussed? For example, hydraulic conductivity. That is an aquifer property. What else did we discuss? We discussed about transmissivity, permeability, specific storage, storativity, specific yield, specific retention, right? So these are different aquifer properties that you need to know when we are discussing about the groundwater flow, right? So the definitions are important. You have to know exactly what it is, right? So that was one part that we discussed during the last class. Then we discussed about the groundwater flow equation. The basic equation that you learn is the Darcy equation. After that, we combine this Darcy equation and the continuity equation together to develop the three-dimensional groundwater flow equation. That three-dimensional groundwater flow equation is the most general form of the equation for the groundwater flow. It can account the steady and unsteady flow, homogeneous, heterogeneous aquifers, isotrophic and isotrophic aquifers, three-dimensional, right? So that is the most general form of the groundwater flow equation. Then you learn that that equation cannot be applied in simple, like in a cases where you have very limited information. So what you do in that case, you simplify that three-dimensional groundwater flow equation by using certain assumptions so that it can be maybe 1D equation or 2D equation. So you learn how to simplify that three-dimensional groundwater flow equation using certain assumptions. Those assumptions can be the unsteady flow equation can be assumed as the steady, or the heterogeneous aquifer can be assumed as homogeneous. Anisotrophic aquifer can be assumed as isotrophic, right? So like that, using those assumptions, you can simplify the three-dimensional groundwater flow equation. So that is what we discussed. Then we discussed a couple of examples, right? So that is what we did during the last class. So today I'm going to discuss about the radial groundwater flow equation. Radial. When we discuss about the three-dimensional groundwater flow equation, we use the Cartesian coordinate system, X, Y, and Z. But today I'm going to discuss how it will be different when we use the radial groundwater flow equation, radial coordinate system, right? Then we will go in detail about the pumping test. This pumping test is a test that we do to find out the aquifer properties. Properties like the hydraulic conductivity, then the specific storage, and isotrophy, right? So this kind of aquifer properties can be found by using this pumping test. Then if I have the time, I will talk about some application of this pumping test. When you are going to apply the pumping test in the field, what are the challenges you will have and how you are going to overcome these challenges. All right. So these are the things that I am going to discuss today. Do you have any questions so far? Perhaps any question from the previous class?
No, sir.
Okay, good. Right. So we will continue there. Now about the radial groundwater flow equation. Now think about an aquifer. If you want to discuss about the head at any point in this aquifer, and if you are using the Cartesian coordinate system, you will use X, Y, and Z. Let's say we are talking about a horizontal plane. Then if you want to talk about a point somewhere here, you can use the X and Y in the Cartesian coordinate system. But here, if you are talking about the radial, then you can use the R, that is the radius, and angle, R and theta, right? So that is the main difference between this Cartesian and the radial coordinate system. Now, if you can assume the aquifer is infinitely large, meaning is that there are no barriers on the way, and if you have a pumping well like this at the middle of the aquifer, then when you start pumping water out, what happens? The water start coming into the pumping well from all the directions, right? So that we can consider this case as a symmetric case. In that case, we can use this radial coordinate system to simulate this groundwater flow field. That is the basic idea. So that if you consider a cross section of this one, it will be like this, right? So this is the cross section of this previous figure. Now what happened is that here we have the pumping well, and when you start pumping water out, what happened? This is the original piezometric head. This original piezometric head will start going down. That is what we call the drawdown, right? So the drawdown will increase with the time. And there will be a stage where the drawdown does not change anymore. At that time, we call that the system has become steady. For example, in the beginning, this is the original groundwater piezometric head. Why I call it is the piezometric head? It is because here we are talking about a confined aquifer. In the confined aquifer, this piezometric head is something that you cannot see physically, right? Piezometric head is equal to the pressure head plus the elevation head. And it is a pressurized aquifer, right? So that you can see it only if you drill a well so that the water level will rise to this level. So that is the indication of the piezometric head in this confined aquifer. What is the confined aquifer? It is an aquifer in between two impermeable layers, so that it is a pressurized aquifer. So if you drill a well, then the water level will rise up to this point. That is the piezometric head. So this is the original piezometric head. When you start pumping water out from this one, what will happen? This piezometric head will start changing like this. That gradually increase, this drawdown gradually increase with the time. Then there will be an stage, this drawdown doesn't change anymore. So that state, we call it is the steady state. Now we write this equation for the steady state. This is the assumption. And it is a confined aquifer. So we want to understand how our equation will be different when we have a confined aquifer and when the flow is steady. Right? So as usual, we use the continuity equation. We can write Q is equal to AV. What is special about this A and V? A is the cross-section area, V is the velocity, average velocity. So this A and V are perpendicular to each other. If this is your cross-section, then the flow rate should be perpendicular to this cross-section, right? So now, think about this aquifer now. Water is coming from all the direction like this to this well. So that at any point, if you consider the water flow rate to this well, then what is the cross section that you should consider? It is like this. Think about it as a cylinder. Now, this is the cylinder. You have this pumping well at the middle. So you are pumping water out from this. Therefore, the water is coming from all directions to this cylinder. Therefore, if you consider this radius, this is R, and thickness of aquifer as B, simple B is the saturated thickness of this confined aquifer, then the cross section become 25R. 25R is the perimeter, 25R multiplied by B. That is the cross section area. So A is equal to 25RB multiplied by Darcy velocity. V is the velocity, average velocity. How do you write average velocity? K dH over dr. That is the Darcy equation, right? So that is all what you need. You have this equation, the general equation now. What you can do the integration one time with certain boundary condition to find out the relation between the pumping rate and the aquifer properties. It is that simple, right? So that just do integration one time. What are the boundary conditions that we use? See here, we can consider two boundary conditions. The first one is, what is the head at this pumping well? You see, the drawdown has now become steady. So at this point, the head is HW. So our first boundary condition is when R is equal to RW. What is RW? That is the radius of the well. When R is equal to RW, H is equal to HW. That is our first boundary condition. The second boundary condition is our initial piezometric head. You see now, there is a distance in this aquifer that it will be affected from this pumping. There is a distance. After that point, there will be no influence from this pumping to the aquifer. That is we call the radius of influence. Radius of influence. So what it is, in this case, this is the radius of influence. That is we call the R naught. Beyond this point, there will be no change of the piezometric head because of this pumping. All right. But before that, for example, in this region, of course, it has affected. But in this time, in this distance, there is no effect from the pumping. Therefore, what happens is that when R is equal to R naught, that is the radius of influence, we can say H is equal to H naught. What is this H naught? That is our initial piezometric head. Right? So that's it. We have two boundary conditions and simple equation to integrate. Do the integration, you can get this equation. I'm not going to show you how to get that. This is a very simple integration, right? So do the integration by yourself, you get this equation, right? So what is the special about this equation? Now you see, if you can measure the pumping rate, of course you can measure it, right? It is a pumping test. So during the pumping test, if you can measure the pumping rate, and if you can measure the piezometric head and the radius, then simply you can find out the hydraulic conductivity. That is the pumping test, right? A very simple formula. So by measuring the pumping rate, then the radius and the piezometric heads, you can find out the aquifer properties. Now, the same equation has been written in a different form. What it is, we know that saturated thickness multiplied by the hydraulic conductivity, that is equal to the transmissivity, right? So instead of B and K here, we use the T, that is the transmissivity, right? Same equation, but in a different form. So the transmissivity can be found by knowing the flow rate, head, and the radius. So this equation is called the theme equation. So the researcher, theme, is the first who developed this equation, theme equation. And you need to remember under what condition we can use this theme equation. What are the assumptions? What are the conditions we use? What did we use? We assume that the flow is steady and it is an confined aquifer. Other than that, there are many other assumptions. For example, we assume that this piezometric head originally is horizontal and the aquifer is largely infinite aquifer. There are no boundaries, right? Like that, there are several other assumptions. Okay. So do you have any questions? Is it clear?
Yes, sir.
Right, great. Now, when we use these two boundary conditions, you need to understand practically, it is not an easy thing to know this second boundary condition. When R is equal to R naught, H is equal to H naught. So you need to understand what is the distance being influenced by this pumping. But without having several observation wells, you cannot know where is this radius of influence. Therefore, instead of that, what we can do, we can have two different other boundary conditions. In this case, what they have done, now this is the pumping well. They have two observation wells. These are called the observation wells. So during a pumping test, normally we use at least one pumping well and two observation wells. It is recommended to use at least two observation wells, but normally we use even 3 observation wells. So the more that you have, it is the better. But if the fund is limited, you can use 1 observation well. All right. So now in this case, what we can do, we can use these two boundary conditions. What are they? When R is equal to R1, you see this one, R1, H is equal to H1. That is our first boundary condition. Second boundary condition is when R is equal to R2, H is equal to H2. That is all what you need. You just need two boundary conditions. The same equation, apply these two boundary conditions, you can get this equation. Right? Now, we try to simplify this again further. You see, if you want to measure this head, measuring the H1 is difficult because the H1 is the depth from the impermeable layer to the water level in this well. That is difficult to measure. Instead, what we can do, we can measure the water level from the ground surface. Let's say this is the ground surface, water level from the ground surface to the water level in the well. The depth from the ground surface to the water level in the well, that we can measure. Therefore, by knowing original groundwater level, the depth to the original groundwater level, we can find out this one. This is called the drawdown. So you see, this is the drawdown for this well. This is the drawdown for this well. Drawdown is what? That is the depth from the original groundwater flow level to the current groundwater level in the well. That is the drawdown. Right? In other words, the change of the piezometric level because of the pumping. Right? So that now you can see this, let's say S1, simple S. All right? We use simple S for the drawdown. Simple S1 you can write, that is H0 is the original groundwater flow head minus H1, that is S1. S2 is equal to H0 minus H2. So that you can substitute in this equation and write the same equation in terms of the drawdown. Earlier we wrote it in terms of the piezometric head. Now we can write this equation in terms of the drawdown. Right? So depend on the given information, depend on the given boundary condition, you should be able to rewrite this equation. What is important is you to know the basic behind it. This is the basic. Right? You apply the continuity equation, Darcy equation, that's it. Then do the integration one time, depend on the given boundary conditions, depend on the given data, you simplify the equation. Right? So I hope it is manageable. Right. Now we will talk about the steady flow in unconfined aquifer. Earlier what we discussed, it is a confined aquifer. So the theme equation is applied for a confined aquifer. Now, still the flow is steady, very important assumption. Flow is steady, but we are applying it in an unconfined aquifer. Now, I need you to compare these two figures, this one and this figure and tell me what is the major difference between these two aquifers. Can someone tell me what is the major difference? Nobody? Okay.
So can't hear question.
My question is, now you can consider this confined aquifer, this one. And this is the unconfined aquifer.
Yes.
So I need you to tell me what is the major difference between these two aquifers when it comes to the governing equation.
Confined aquifer in between two permeable layers.
Yes, exactly. Very good. Then?
But unconfined aquifer, one permeable layer.
Very good. And the ground surface. It is the aquifer
Yes,
between
yes.
ground surface and one impermeable layer.
Yes.
Now, when it comes to the governing equation, what will be the major difference here? You see, when we talk about the confined aquifer, we consider this B, simple B, that is the thickness of the saturated layer, as a constant. This one doesn't change, even though the piezometric head change with the time or from place to place. Still, this simple B is a constant, saturated thickness. So when you are writing the A, that is the cross-section area perpendicular to the velocity, that is, this B is going to be constant. But now you see what happened when we are talking about an unconfined aquifer. See, this H is the saturated thickness now. This saturated thickness change with the R. Change with R. Right? So that is the major difference. So that now the equation is becoming little bit complicated. Why it is? Because we will have H as a variable when we write cross-section area. So what is our cross-section area? Let's say you consider a place somewhere here. What it is? If you see it from the top, you have this kind of a circle. Your pumping well is at the middle. This is your R, radius. And H is the thickness. So again, what you have? 25R is the perimeter multiplied by H. That is the area. Area then multiplied by the Darcy velocity, V, it will give you the flow rate. Again, a simple equation. Only different there is that now instead of B, we have H. That is the difference. So that H and dH over dr, both are variables here. Right? So that you do the integration again one time for this equation. Then you can find out a relation between the flow rate, hydraulic conductivity, radius, and the water level. Right? So again, very simple. What you need to do is to use a couple of boundary conditions. It can be the H when H is equal to H naught, or hydraulic head at the radius of influence, or it can be where H is equal to HW, water level at the well, or it can be H1, H2. Somehow what we need is two boundary conditions. You can find out the hydraulic conductivity, right? So I hope you are clear with the major difference between the confined and the unconfined aquifer. All right. So just the equation become little bit complicated when it comes to the unconfined aquifer. Right? Okay. So now we will go for a practical case. You see, we don't find confined aquifer with a very simple setup all the time. That aquifer can be unconfined. In addition to that, sometimes we may find that we have this kind of a recharge from the top. What kind of case it is? The first thing is during the pumping, it may start raining, right? Normally the pumping test continue for a couple of days so that the rain is expected. That is the first thing. The second thing is that maybe it is an irrigation land, right? So that you have a constant recharge from the top. So in that case, how do we do it? All right. Now, can someone tell me what is the major difference between this one, this figure, and this one? Look at it very carefully and tell me what is the major difference. I know that there is a recharge from the top, right? That you don't see it in this figure, right? So because of that, what happened? Here, the major difference is when it becomes the steady state, when the system becomes steady, if you consider any cross section, the water comes to that cross section is going out from that cross section. For example, if you see this cross section from the top, the Q flow rate is coming in and the Q is going out and come to the well. The same flow rate. And that Q is going out from the pumping well. Right? So that is the case when the flow is steady in an unconfined aquifer. But now what happened? We have this kind of recharge from the top. Therefore, if you consider a cross section like this, just a cross section, this one, the flow Q is coming in, but what is going out is not exactly the same as Q. That is, we write equal to Q plus delta Q. Why it is? Why more water is added now? Why more water is going out from this small control volume? The reason is we have a recharge coming from the top. More water is added from the top in addition to this water coming from the aquifer. That is the major reason, right? So that we can write this small q, dq, this one, as, so if you see from the top, let's say we have this kind of control volume, our pumping well is at the middle. So now you consider the general case like this, right? So this is this cross section that you consider here, right? So what I have drawn here is how you see it when you see it from the top plan view. Now, see what happened. If I consider this distance as R and thickness of this one as dr, then this small amount of water added, the extra amount of water that is going out from this control volume dq, I can write in terms of this recharge rate. What is this recharge? That is the amount of the water volume that we add from the top per unit area. Water volume per unit area. All right. So that what we can do, we can write this dq in terms of the W. So the dq will be equal to the W, that is the flow rate per unit area, multiplied by this area. This area. So what is this area? That is equal to 25R. 25R is the perimeter multiplied by dr. Right? So that's it. So this is equal to dq. Now you see there is a negative sign here. Why there is a negative sign here? Because this W is to the downward, to the down. But we consider positive is to the upward side. That is why you have a negative sign here. And that's it. So you have one equation now. Do the integration one time. It come up with the constant. C is the constant. Now we use a boundary condition. What is that boundary condition? When R is equal to 0, R is equal to 0 here. Q is equal to QW. That is the flow rate at the pumping well. That is the flow rate that you are pumping water out in this case. So that is our first boundary condition. When R is equal to 0, Q is equal to QW. So we substitute it to remove the constant C. We find out C by applying this boundary condition. This one. Then we need one more equation. What is that equation? Simply we can use the Darcy equation. Right? Similar to the previous case, similar to this case, we use the Darcy equation. Right? The same equation. This one. So now you see, if you consider this equation and this one, we have the Q from the both sides. Therefore, the right-hand side of the both equations are the same. Right? Now you have one equation in terms of the QW, that is the flow rate that you are pumping water out. W, that is the constant recharge rate. R is the radius, hydraulic conductivity. That's all what we need. Right? So do the integration just one more time with the boundary condition. For example, when R is equal to R naught, H is equal to H naught. Or what you can do, you can find out when H is equal to H1, R is equal to R1. Right? Water level at an observation well. When R is equal to R1, water level is H1. Like that, you can use any boundary condition you like and solve the equation. Right? So it is not necessary that you use the same boundary condition all the time. You can say when R is equal to R2, H is equal to H2. That is one boundary condition. Right? So that you come up with the equation to find out the hydraulic conductivity when you know the flow rate and W. Right? So that is the idea. Is it clear?
Yes,
Do
sir.
you have any question? Yeah. Right. So if you have any question, please ask anytime. All right. Okay. Now what I discussed so far is some very basic equation, a set of very basic equation under certain assumption. What we assume always is that the flow is steady. Flow is steady. This is the confined aquifer. And here the flow is steady, but this case is an unconfined aquifer. So what I am going to discuss now is how do we write this radial groundwater flow equation when the flow is unsteady? It is not steady anymore. Meaning is that when you start water pumping out, then the drawdown change with the time. So now you are talking about that state. For example, original water level is here before you start pumping water out. With the time, this drawdown curve change like this. So now I am talking about this state. Water level change with the time, or the piezometric head change with the time. That state. So during the pumping test, we take these readings with the time. How the piezometric head change with the time. If it is an unconfined aquifer, how the water level change with the time. We take these readings. So what I'm going to discuss now is that how you derive an equation for this state. All right. So that is called the unsteady state. This is where your understanding about the aquifer properties is important. All right. Now, in this case, if I again consider a general case like this, now this is the, let's say, radius of influence. I have the pumping well at the middle, and I consider a general R like this. All right. So when the flow is steady, the Q comes to this one, this small control volume, and the Q going out from that one is the same. Right? When the flow is steady. But now we are talking about unsteady flow. So the profile, piezometric head, or the water level is still changing. Why it is changing? It is because the Q that come to here and Q that is going out from this one are different. That is why the water level is still decreasing. Right? So we use that logic here. So the flow rate difference, net flow rate, is equal to Q plus delta Q minus Q. Right? So that should be equal. How do we write it? What is the aquifer property that we use? We use this capital S. Can someone tell me what is the capital S? What is the aquifer property? Anyone? What is the aquifer property for this S? Nalinta? What is the aquifer property? Represented by S. That is called the storativity. Right? Storativity. What is this storativity? That is the volume of water that you can pump out or you can recharge, re-inject into an aquifer per unit area when you are changing the head by 1 unit. When you are changing the head by 1 unit, let's say 1 meter, what is the amount of the water that you can pump out? Or what is the amount of the water that you can inject into the aquifer per unit area? So you are talking about a water volume per unit area when the head change by 1 unit. That is why the storativity is dimensionless. Right? So now we are talking about the water volume here. So what we can do to find out the water volume of this area, what we can do? We can multiply it by the respective area here. What is that area? 25R dr. Right? 25R dr is this area. Then what is the head change? We have L here, right? Per unit change of the head. So the head change here is delta H. So when you do that, this part here will give you the water volume. that you pump out because of this head change. Then we are talking about the flow rate here. So the water volume divided by the time will give you the flow rate. So that is the major equation, right? So now you have this derivative equation, right? So one more time, you use the Darcy equation. Darcy equation one more time. Here we are talking about an confined aquifer. You see, this is an aquifer in between two impermeable layers. So our thickness, saturated thickness is constant, right? Now what we do? We have Darcy equation, but here it is left-hand side you have Q. But in this first equation, we have dQ over dr. So what we can do, we can take the derivative with respect to the R one time of this Darcy equation. So dQ over dr, we can write it like this. You need to remember, here there are two variables, R and dH over dr. So you need to take the rule of derivative multiplication. When you do that, you come up with this equation. I'm not going to elaborate more because of the limited time. All right. So I hope you can manage it. Just consider the multiplication rule of the derivative. You can get this equation. Now you have two equations. This is the first one. This is the second one. Both sides you have the dQ over dr. Therefore, you can write this one, get this equation. All right. So the same equation, we can rewrite it like this. Right. So this is called the most general form of the groundwater flow equation in the radial coordinate system. All right. Do you have any questions?
No, sir.
No. Okay. Right. So let's move on then. Right. Now we are going to use this radial flow equation for the pumping test. Right. So because before that, I will discuss briefly about this pumping test. The pumping test, what we normally do is we drill a well that we use for pumping water out. In addition to that, we drill a couple of observation wells. This can be the first observation well. Somewhere here, there can be another observation well. All right. So now, there is a difference between the head that we calculate using mathematical equations, a simple mathematical equation, and actually what we observed at the field. Why it is? Because in the field, this head is affected by several other factors. We call them the head losses. What are they? Now, when we install a well, there is a region where the water comes to the well. That is, we call the screen. So in this well, this is the depth that we have screens. This one. This part here in the well is totally covered. Therefore, no water come into the well from this region. Only from this region that the water comes into the well. That is, we call the screen. So these are the screens that you see in this figure. Right? But this region, you see, there are no screen. So that the water cannot come in. Now you see, these screens are very, very small. So that when the water flow through a small area, then there is a head loss that it generates. So this head loss is not normally accounted in those equations that we discussed earlier. Right? So that can be one effect. One reason where you get some difference in your estimations, right? So the head loss because of the screen effect. In addition to that, you see near to this is how the piezometric head profile change with the distance. That is, we call the drawdown curve. This drawdown curve is very steep near to the pump-in well. You see, near to the pump-in well, the gradient is quite significant. But somewhere here, gradient is very mild, right? So the gradient is higher mean the velocity is higher. When the water velocity become higher, you have learned in pipe flow, for example, head loss is proportional to the velocity. When the velocity is higher, head loss is higher. So the flow can become turbulent near to the pump-in well. Therefore, the head loss can be higher than what we expect. Probably you remember we discussed that the Darcy equation is applicable only when the Reynolds number is less than 1. Right? But that condition may not be satisfied near to the pump-in well if the flow is turbulent. Right? So those are some limitations of this pump-in well. Right? But there are many equations, even some analytical equations are available so that you can include these head loss terms. Numerical model like ModFlow can certainly incorporate these head losses so that more accurate result can be expected. All right. Yes. Now we will move to the history of the pump-in test. All right. So the equation that we discussed earlier, team equation, was the first equation developed for the pump-in test. But you need to remember, team equation was developed under some certain conditions. Right? So what are these conditions? Team equation, we consider that the aquifer is confined, then the state is steady state, pump-in rate is constant, right? So those were the assumptions that we use, right? Then later on, I will discuss another equation that is called the Thies equation. This is the team equation developed in 1906. This is the Thies equation developed in 1935. So this is the first analytical solution developed for the transient state. What it is? Unsteady. Transient means unsteady case. So this equation was developed for the unsteady state. And the pumping rate is still constant. What is the aquifer? It is an confined aquifer. Later on, researchers developed many analytical solutions to address these assumptions. For example, here we assume that the aquifer is confined. Later on, researchers develop analytical solutions. What happens when the aquifer is unconfined? Again, we assume that the aquifer is homogeneous. If it is not homogeneous, how the heterogeneous case is addressed? Also, we assume that the aquifer is isotrophic. If it is an anisotrophic aquifer, how it is being handled? Like that, researchers develop several other analytical solutions to address these limitations. All right. So what is important is you to know exactly what are the assumptions behind these analytical solutions. So for example, if you take the Thies solution, what are the assumptions? Team solution, what are the assumptions? Right? So very important you to know. Otherwise, it can produce very different results. Okay. Right. So this is Thies, Professor Thies. All right. So this equation can be used only under these assumptions. All right. So Thies, what he did, he developed an equation to estimate the transmissivity and the storativity of a confined aquifer under the non-equilibrium. Non-equilibrium means unsteady, or the transient flow equation for the considering the radial flow condition. Right? That is the thesis equation. So what are the assumptions he used? He assumed that this well fully penetrate the aquifer. What is the meaning here? Fully penetrating. Suppose that we have a confined aquifer like this, two impermeable layers. Remember earlier I told you in this well, there is a region that we have the screen like this, and there is a region that we don't have the screen. So here the fully penetrate mean the well penetrate fully into the aquifer like this. Not only that, we have to have the screens covering the entire depth. That is we call the fully penetrating an aquifer. So that the water comes from all direction into the well like this. So the whole depth contribute for the groundwater flow. That is the fully penetration case. The second is that the aquifer is confined and homogeneous. Of course, it is a confined aquifer and homogeneous. What it mean? Homogeneous mean that is the opposite to the heterogeneous. Homogeneous mean hydraulic properties does not change from place to place. Right? So it is an homogeneous case. Then the aquifer is of an infinite extent. What it mean? No boundaries. What kind of boundaries can be seen? For example, you may have the pumping well here, and somewhere here, you will find out that there is a river, or a lake, or a wetland, or the ocean, or an impermeable rock that may add water into the aquifer, or it may block the water flow into the well. Right? So those are the boundaries. So we assume that the aquifer of an infinite extent, infinitely large, meaning is that there are no boundaries. That is a major assumption. It may not satisfy the existing boundary condition, existing site conditions. So in this lecture note, I have added some slides near to the end that will show you how to handle this kind of complex site conditions. All right. Okay. The last boundary condition is that the well is of an infinitely small radius. This well radius is very small compared to the radius of influence. What is the meaning of that? Compared to the amount of the water that comes from the aquifer, the water volume that we have inside the well is very, very small. Therefore, this water volume inside the well can be neglected compared to the amount of the water that comes to the aquifer from all the sides. So that those are the assumptions made by this solution. So you need to remember them. All right. Then only you can apply it in the field. Right. So how do we do it? So this is a real case. I was there when we do this pumping test. This is in Oman, in Muscat Airport. All right. So we were asked to do, actually it is a big project, and part of that project is to do the pumping test to find out the aquifer properties. Right. So this is the pumping well. Here we have the pumping well. Here we have one observation well, and somewhere here there was another observation well. The second observation well, you don't see it in this figure. All right. So how do we do it? Right. It is very important you to know what are these steps. So what we do, measure, draw down at different values of T at once or more. Meaning is that you take the drawdown as you pump the water out in different times. So normally this pumping test continue for a couple of days. For example, in this project, we continue pumping for a 1 day and we stop, and there is another test called the recovery test. That recovery test was continued for another 12 hours. So altogether 36 hours continuously we took the readings. I have seen in Canada, there was a case that the pumping test was continued for 1 week, whole 1 week. All right. So then only you can assume that the flow reach to the steady state. Okay. So take the drawdown with the time. That is the pumping test. So it consists of taking readings of drawdown versus time at one or more radii. We have the pumping test here so that we take the drawdown versus time readings here. For example, this black color values that you see here in this graph are from this pumping well. Then we also measure the drawdown versus time in observation well. So this blue color one is the observation at this well. And there was another one somewhere here. Right? So we take the readings in the pumping well and observation wells. Discharge Q is measured and kept constant by suitable adjustment of pump speed or outlet valve opening. So this pumping rate must kept constant all the time. So in this project, we use a water meter, piezometer, and a V-notch to guarantee a constant pumping rate. So we need to measure it all the time to make sure that the pumping rate is constant. When we start this pumping test, we take the readings at the beginning at very small time intervals. For example, we start with like 15-second intervals. We take the readings. Now you can see there are many readings near to the beginning of the pumping test. But as the time passes, we increase that time interval to 2 minutes, 5 minutes, 15 minutes, 1 hour, like that. We increase the time interval. The reason is the drawdown becomes smaller as the time passes. With the time, drawdown becomes smaller. Therefore, it is okay to increase the time interval of the measurement. Right? So the duration of total pumping depends on the available time and the rate of drawdown. And therefore, it can vary from like 4 hours to 2 weeks. It is possible. So the time of stopping of the pump must be noted, and after that, as the level comes up, recovery phase reading must be taken until the level reaches almost to the initial level. Now you see in this test, from here to here, it is called the pumping test. You pump the water out. At this point, you stop pumping. So that what happened? Recovery stage start. Drawdown significantly start reducing. What happened? The water level start recovering. That is we call the recovery test. This recovery test can be used as an independent test to verify the estimation that you get from the pumping test. You get some estimations from the pumping test for the hydraulic conductivity or the transmissivity. So that transmissivity can be verified independently by using the data from the recovery test. What is this recovery test? Simply, you take how the water level recovers. In other words, you simply keep taking the drawdown values. That's it. So that you can use as an independent test to check the hydraulic conductivity estimation that you made from the pumping test data. So those who are interested about it, please read this journal paper. I have given you the link. All right. So more detail can be found there. All right. So that is the procedure of this pumping well, pumping test. So what I'm going to explain you now is the theory behind it. Okay. So as I said, this is the most general form of the radial flow equation that we discussed earlier. So the this equation is what he did. He used this equation and he developed this one, which gives you the relationship between the time drawdown and the aquifer properties. So this is called the Thies equation. Thies equation, right? So it is not very simple equation. You see, kind of a complicated one. So what is the logic behind this, right? So what are the parameters we have here? The simple S is the drawdown. And we have here constant pumping rate Q. T is the transmissivity. And this WU is called the well function. WU is called the well function. This well function can be written like this. This is the well function. Right? Sorry, this is the well function. This one, up to here. This one is the well function. All right. So this well function comes with a parameter that is called U. So this U is equal to the, like this, R squared capital S over 4 capital T simple t. So what are these? S is an aquifer property. What is it? That is the storativity. Storativity. R is the distance from the pumping well to the observation well. We have the pumping well here, observation well somewhere here. So what is the distance from the pumping well to the observation well? That is R. Capital T is what? That is the transmissivity. Simple T is the time since the pumping began. That's it. So now you see, by knowing the drawdown and by measuring the time and also by measuring the flow rate, pumping rate, you can find out the aquifer properties, transmissivity, and the storativity. Right? So that is the Thies equation. To do that, you have to take the measurements. Now you see, suppose that you know U. If you know U, you can find out WU, that is the well function. So assuming that you know U, is what he did. He developed set of values for the well function. So for example, what is the meaning of this 4.04? That is, when U is equal to 1 multiplied by 10 to the power minus 2, U is equal to 1 multiplied by 10 to the power minus 2, WU, that is the well function, is equal to 4.04. That is the meaning of these values in the table. All right? So how do you get this one? Simply you substitute U is equal to 0.01 into this equation, you get the answer. So this, after that, what he did, he developed this curve. This is called the type curve. This type curve. These values that we have in this table, when you plot them, it becomes like this. This is the Thies type curve. So we have the U in the x-axis, WU in the y-axis. How many equations we have? We have just 2 equations. What are they? This is the first equation. Drawdown is equal to Q over 4.5T multiplied by the well function. Second equation is the equation for this U in terms of the aquifer properties. So these are these 2 equations, just written in a different form. Right? So now you see, we have a relationship between U and WU. WU and U. Here we have some constants. T is the transmittivity, it is a constant. Q is the pumping rate, it is a constant. S again is a constant. So that if you have a relationship between this WU and U here, we must have a same relation between S and R squared over T from the other side. Why it is? The reason is these are constants. So what these suggest, take another piece of paper, right? Then plot it like this. What it is? Here it is R squared over T. Here it is S to the same scale. All right? It must be into the same scale. For example, from 0 to 1, this distance must be same in here. So plot it like this. So you will have some observations like this. Then match this observation with this curve here so that you can find out the aquifer properties. That is what these recommend. Okay, I will explain how to do it. Now, this is the piece of paper I told you, the graph sheet. What are the values we have? R squared over T and draw down. So we plot our observations here like this. Then these observations are matched with this curve. How do we do it? I will show you one example. Now, during this pumping test, we have taken these readings. What are the readings? Time and the drawdown. So we have the radius as well. So observation well is 60 meters away from the pumping well. And we also have the pumping rate. So what we do, we plot the relationship between S and R squared over T. R is the radius, T is the time, right? So we calculate this one based on this one and this radius. Then we plot R squared over T versus drawdown. When you plot it, it will be like this. Now you see these small circles that you see there, they are the observations. When you go home today, I need you to try to plot them. Then compare it with the T's type curve. T's type curve, you can download it over the internet. They are available. Then compare them. You should be able to get a plot like this. Now you see there are two graphs. This is the graph 1, that is the T's type curve. This is the graph 2, that is the observations, based on the observation. So what you do, you move this one to the left or right, up or down, until you get all these observations on top of the T's type curve. You get the best match, right? So according to this, now this is the best match. What we do next? We select any convenient point. Any convenient point. For example, you can select this point here, or point somewhere here, or point somewhere here. Any convenient point should be okay. So what I will do in this case, I will consider point here. What is the special about this point? It is because when I select this point, my WU is equal to 1, U is equal to 10 to the power minus 2. They are round numbers, right? So that is the convenient. Otherwise, if you consider a different point, it also should give you the same answer. So now you see my U is equal to the 10 to the power minus 2. WU, that is the well function, is equal to 1. I also find the corresponding R squared over T value here. That is 150 according to this match. And my drawdown S is equal to 0.18. That's it. I read these numbers from the graph based on my selected point and substitute to the equation. So what is my first equation? It is this one. What I need? I have the given flow rate, that is 2500. I have WU that I got from the graph that is equal to 1, 4, 5. S is the drawdown that is 0.18. So I substitute them. I have my transmissivity value. Very easy. Then I go to the second equation. What I need? I need the estimated transmissivity value earlier. And I need the U value, that is 10 to the power minus 2 R squared over T, that I have in here 150. Make sure that you use the correct unit. This is in meter squared per minute, but I have the transmissivity in meter squared per day. So I change it to meter squared per day. Right? Then substitute it here. I have the storativity value. That's it. Something very simple. Right? Do you have any questions?
No, sir.
No, everything clear. You guys are very smart. Right. Okay. So then I will continue. Right. Let's take like a 5-minute break. All right. So now the time is 2:35. I'll meet you at 2:40. Okay. Just a 5-minute break. Right. Let's start again. Now we discuss about the TC equation in detail. Now, after this TC equation, Cooper and Jacob try to simplify this TC equation. TC equation, even though the method seems simple, the shape of this equation, it is like a parabolic equation, right? So the T's try to, the Cooper and Jacob, they develop a method to simplify this equation. But it comes with the drawback. What is the drawback? It is applicable only under certain conditions. Now, this is the original TC equation, right? So, what Cooper and Jacob suggested is to assume this equation can be simplified like this. So, is it reasonable to assume it like this? If you assume it like this one, that means you are forgetting this part of the equation, which may not be true. But this is valid only if this U is very small. For example, if the U is less than 0.01, then you can see this part of the equation become very, very insignificant. Then only you can assume equation like this. So this is what Cooper and Jacob suggested. Cooper and Jacob said you can neglect this part of the equation, this part, if the U is very small. So how it will become small? You have to have a smaller R. What it means? The distance from the pumping well to the observation well should be smaller, and the T should be larger, so that the U will be smaller. This is what you need to check before you apply the Cooper and Jacob method. You need to make sure that for all the values that you use this test, the U should be less than 0.01. Right. Now, suppose that we have this condition satisfied. Then we work with this equation, simplified equation. Right? So here we have the ln. So what Cooper and Jacob did, they wrote the same equation in terms of the log, in the log form. So what is the relationship between ln and log? Anyone? If you can write ln, any value, let's say that value is x, that is equal to 2.3 times log same value. All right. So for example, substitute ln 10. ln 10 will be equal to 2.3. Log 10 is equal to 1. Right? So that's it. So they wrote the same equation in the log form like this. Right? So this is the Cooper-Jacob equation. Then the same equation can be applied to a different set of readings. So they wrote the same equation for the S1, S2. What are the S1 and S2? Those are the drawdown values at T1 and T2. Right? Then they just simplified this equation like this. I'm sure you can manage it. All right? You are smart enough for that. The same equation, right, for S is equal to S1 when T is equal to T1. And S is equal to S2 when T is equal to T2. You come up with two equations. Then take equation 1 minus equation 2. That means you can come up with this equation. The same equation you can simplify like this. Right? So this is the Cooper-Jacob equation applied for set of readings that you can use to find out the transmissivity. All right. So I will show you how to use this equation to find out the transmissivity. So the same set of readings. Now you can see this equation. It is that equation that we have here. You can write, it is a linear equation. It is not a parabolic shape anymore, right? You have the S here, the drawdown, and the log T here. Others are constants. So if you can develop a relationship between the drawdown and the log T, it should be a linear equation, right? So what we do now, we take a log paper. Yes, actually it should be a semi-log paper. Only the x-axis is in log scale, right? X-axis is in the log scale. Sorry, please give me 1 second. Yeah, right. So the x-axis is in the log scale, y-axis is in the normal scale. Why it is? According to this equation, S is in the normal scale, T is in the log scale, right? So you plot the values and then you plot a best fit line. This black color continuous line is the best fit line. These values that we have here are the readings, drawdown and the log T. So you plot it. Then what you do, you find out the gradient, right? Also, when you find out the gradient, you find out in a way that it will make your calculation easier. For example, we have the log scale here. This one, log T2 over T1. So if you consider this delta S, that is S1 and S2 for a 1 log cycle, then it will make your calculation easier. What is the meaning of 1 log cycle? You find out what is the drawdown when time is equal to 10. What is the drawdown here? Also, you find out what is the drawdown when time is equal to 1. So T1 is equal to 1, T2 is equal to 10. So that is called 1 log cycle. So why it is important? Log 10 over 1 is equal to 1. Right? Log 10 is equal to 1. That is why it is easier. Right? So find out what is S1 and S2, substitute, you get the answer. That is the Cooper-Jacob equation. Something very simple. Right? So you substitute it into this equation, you get the answer. You find out this delta S for a 1 log cycle. That log cycle can be 1 and 10 or it can be 10 and 100. 10 and 100 also one log cycle, right? So in that case, you find it like this. 100 is here, right? So what is this delta S? Log 100 divided by 10 is equal to log 10. Again, it is equal to 1. That is why it is easy, right? Yeah, so you do that so that you can find out the transmissivity. Then what you do? You use now you see when you plot this equation, somewhere here, it intersects with the x-axis. What it means? That is the time when the drawdown is 0. From this point onward, the drawdown start to happen. What it means? It means we have the pumping well somewhere here, and we have the observation well somewhere here. When you start pumping water out, you can see an immediate drawdown change in the pumping well. But it will take some time this effect to appear in the observation well, some time. That is the time that we have here. After this time only, the drawdown start changing in this observation well. So we use that logic with this equation. What is it? Here, this drawdown is equal to 0 until time is equal to T naught. Only after that, the drawdown start. Until T is equal to T naught, the drawdown is equal to 0. That's it. So now you see our drawdown is equal to 0. So the only way this drawdown can be equal to 0 is this part of the equation becomes 0, because others are constant. So log something is equal to 0 means that something should be equal to 1. What is inside this log, it should be equal to 1. Log 1 is equal to 0, right? So in other words, this 2.25 capital T T naught over R squared S should be equal to 1. That's it. You have calculated the transmissivity earlier. You know the T naught from the graph. R is the radius, so that you can find out the storativity, right? So that is the idea. So you have this transmissivity calculated earlier, 1144. T naught coming from the graph, that is in here. R is given radius. You find out your storativity. That is the Cooper-Jacobi equation. All right. Remember, you use it under certain condition. What is this condition? That is, U should be smaller, should be less than 0.01. Okay. Right. Do you have any question? Are you listening or are you around? Is it clear or not?
Clear, sir.
Right. Clear. Very good. Right. So we talk about two solutions, this solution and the Cooper-Jacobi solution, to find out the transmittivity and the storativity with the transient data. Right? So I told you, when we do a pumping test, we stop pumping and then we keep taking the readings, time and the drawdown. That is we call the recovery test. Right? So this is the water level, how it goes down during the pumping test, pumping period. Right after you stop the pumping, water level start recovering. Water level again increases. That is we call the recovery period or the recovery test. Right? So that there is a theory behind it. We depend on the principle of superposition. We use the principle of superposition. You can check what it is exactly on the internet. Principle of superposition. All right? So that we use to simulate this effect of drawdown change during the recovery period. All right? I'm not going to explain in detail what is the effect of that. You can read it in your booklet because of the limited time. All right? But I will explain how it can be used to estimate the or verify the our estimation from the pumping test. So here what we do, now this is the equation for the recovery test. All right? What we need is S dash. What is this S dash? S dash is the, we call it is the residual drawdown. Drawdown is simple S. Residual drawdown is S dash. What it is, that is the drawdown during the recovery period. Drawdown during the recovery period. So you take this measurement and T dash. T dash is the time since the recovery test started. Be very careful. T is the time since the pumping test was started. T dash is the time since the recovery test was started. For example, if you are talking about a time somewhere here, this is your T dash. But this is your T. T is the time since the pumping test was started. T dash is the time since the recovery test was started. S is the drawdown. S dash is the drawdown during the recovery period. That's it. That is all what you need to remember. Right? So the equation is like this. That is also a linear equation. If you use S dash and log T over T dash. Right? So what you do, you plot it like that, then find out the gradient. You see, gradient is equal to this one. Very simple. Right? This is your x-axis, this is y, and this is the gradient. What you get is y is equal to mx kind of an equation. M is the gradient, which is equal to this one. So you find out gradient and make it equal to that 2.3 Q45 delta S dash. That's it. Right? So that you have transmissivity estimated. That transmissivity that you estimate using the recovery data can be compared with the values that you get from your pumping test. But what is the limitation here? You can estimate only the transmissivity using the recovery test. You cannot estimate storativity. Cannot. Only transmissivity can be estimated. That is the limitation. So only transmissivity can be verified by using the recovery test. Okay. So I have given you several examples here. I need you to do one by one and check if you understood it clearly. Right? Plot it by yourself and do it. Okay. That will be helpful for your exam. Right. Now, during this pumping test, I told you we have to keep the pumping rate constant. Right? Pumping rate must be constant. So this is called the constant rate pumping test. Constant rate pumping test. In addition to that, there is another test called the constant head pumping test. We keep the head constant. There is another test that is called the step drawdown test. This is the constant rate test, the observation during the constant rate head. But step drawdown test, what we do, we change the pumping rate time to time. You see, During this period, we have used one pumping rate. So only during this period, the pumping rate is constant. You can see drawdown is very significant in the beginning. Now gradually it is becoming insignificant. Gradually, the change become insignificant. What we do after that? We increase the pumping rate again. When we increase the pumping rate, again there is a significant drawdown. Again, pumping rate the drawdown become constant. We increase the pumping rate again. Again, the drawdown becomes significant. Right? That is called the step drawdown test. So we increase the pumping rate step by step, then the drawdown also change. All right. So that is called the step drawdown test. That is important us to understand how the aquifer responds when we change the pumping rate. So in a real site, especially for the water treatment or the water supply schemes, we do both this pumping test and the step drawdown test, constant rate test and the step drawdown test. Okay. So that is for your information. I am not going to discuss the theory behind this one. Again, the principle of superposition can be used to simulate this effect, but I'm not going for that much of detail because of the limited time. All right. So far, what we discuss is the steady radial flow. This equation is applicable for the steady flow. Unsteady confined aquifer, right? This solution is applicable. This solution is applicable for the unsteady but confined aquifer. Now what I am going to discuss is how this unsteady equation can be applied for the unconfined aquifer. Very important. You don't find the confined aquifer everywhere. If the aquifer is unconfined, how do you apply this pumping test data, right? So this is now becoming a little bit complicated, right? So now, when it comes to the unconfined aquifer, there is something additional come into the picture. What it is? For the unconfined aquifer, let me draw it here. When the aquifer is unconfined like this is the ground surface. This is the impermeable layer. Suppose that we have a pumping well like this. You are starting pumping water out. This is the original water level. Now, when you start pumping water out, what will happen? It will develop a drawdown curve like this. This is the drawdown curve. In the confined aquifer, it is like this. Between two aquifers, you have the pumping well. So you keep pumping water out. But now what happened when you start pumping water out from the unconfined aquifer, this region here became unsaturated. It is like a wet cloth now. It is a wet cloth. For example, think about a wet towel. If you take out from the basket, what will happen? Water start draining down from this unsaturated layer. So this is now acting as a second source of water in addition to this water coming from the aquifer, from the saturated part. Water start coming from the unsaturated part as well. So this is a second source of water to the pumping well, right? So that is the difference. Here, this effect is called the delayed yield. Delayed yield, right? So that is happening in an unconfined aquifer. So Bolton, he developed a series of solution for that. He developed one solution, then he start improving that solution for the unsteady radial flow in an unconfined aquifer. All right. So this is what I'm going to discuss now. Now what happened? Actually, that behavior is like this. Very interesting behavior. So what happened? We have three regions here. The first region happens within a very short period of time. It is right after, in matter of seconds, where you start pumping. Whenever you start pumping, within a very short period of time, even though the aquifer is unconfined, that unconfined aquifer is behaving like a confined aquifer during this period. What happened? The water is coming only from the storage during this time. That is true actually, because still the drawdown has not very well developed. There is a time this water from the unsaturated region to penetrate into the saturated part. So that during first few seconds, you can assume, even though your aquifer is unconfined, that is acting as a confined aquifer. So the water is coming only from the aquifer, saturated part. Still, the delay yield has not started. Then what happened? The delay yield, the water start coming into the well from the unsaturated part. So that you have this part here. Now you see the drawdown is insignificant, become kind of flat, very small as the time pass. The reason is because in addition to the water coming from the saturated layer, water start penetrating down from the unsaturated layer. So there are two sources of water now. Therefore, for that particular pumping rate, the drawdown become insignificant. After that, it become an equilibrium is approach between the gravity drainage and the rate of decline of the water. Then again, it start increasing. So actually, there are now three regions. So we plot different equations for these three regions. All right. So this is the type curve Bolton developed for these three regions. Actually, this is what we expect during the very first seconds, where the unconfined aquifer is acting as a confined aquifer. Then you see that the region here, the curve become flat because of the delay yield. Then again, it increases where it becomes the equilibrium. Right? So the Bolton equation now actually has three functions. This is for the early stage, right? This is for the delay yield. This new can be used to estimate some other aquifer properties that we could not estimate during the TC equation. For example, we could not estimate anisotrophy. So here, anisotrophy also can be estimated for the unconfined aquifer. That is the importance of this solution. All right. I'm not going for a very detailed discussion, and I will ask you to read this given content, but I will show you very quickly how this assumption you must know. I have discussed with respect to the TC equation. So here, this assumption you can understand. All right. So I will discuss one example, exactly how we do it. All right. So again, here also we take the readings. T, that is the time, this is the drawdown. Similar to the previous case, we take these readings and we match it with the type curve. We match it like this. So these again, here also we have the type curve. This is the type curve, right? Type curve. And we plot our observations. This is the time, this is the drawdown in another paper. Here also make sure that the scale is the same. For example, from 0.1 to 1, this is the distance. You must have the same distance here, 0.1 to 1, 0.1, like that. All right? So the same distance, same scale. Then you plot it. Now you can see observations also have kind of 3 regions here. So what you do, you first match with the type curves by considering only the first region. You match it. You forget about these points. You focus only about the first region. Then similar to this solution that we discussed earlier, curve matching, we find out any convenient point. Most of the points should be matched with one of these curves. Then select any point that you like. Here we have well function that is equal to 1 over UA from here that is equal to 1. So we take these readings here and here. We take the reading. That is the drawdown and the time. Similar to the previous case. Then substitute into the equation. Very simple. We have the pumping rate. We have the drawdown that is coming from here. This is the drawdown. Then well function. Well function is equal to 1 here. You can find out the transmissivity. We use the same equation as the TC equation to find out the storativity. Same logic. You can find out the storativity. All right? Then we also can find out the anisotropy ratio. In other words, we can find out the horizontal and the vertical hydraulic conductivities. So we have these equations here. Right? So what you need to do is now match this second part of the equation. Sorry, this later part of this observation with the type curves. How do we do it? We move this graph to the right. This is the type curve. Type curve, we keep it as it is, but the second graph, we move it to the right along the same curve until this third part of the observation match with the type curve. So now you see when nu is equal to 0.06, most of the points in the later part of the equation match with the type curve. Again, we select a match point. T is equal to 10. Drawdown is this one. WU is equal to this one. This is in here. Right? So these are the points we can use again to find out horizontal hydraulic conductivity and the vertical hydraulic conductivity. Right? That is the logic. I'm not going in detail because of the limited time, and since I have explained this equation in detail, the same method can be applied here for the unconfined aquifer as well. So please go through this example and I'm sure you can manage it. All right. Yeah, do you have any questions so far? Our time is very limited. I also need to explain about this boundary effect. You remember we assume when we apply this equation, even the Bolton equation, we assume that aquifer is infinitely large. In other words, we assume that there are no boundaries. But it is not true. There can be boundaries. For example, see, here we have a pumping well when you start pumping water out, we find out that there is a boundary here. What is it? This is a river. So if this river is not here, the drawdown that we expect is something like this. Drawdown that we expect. But because the river add water into the aquifer, drawdown that we get is like this. Now you see, there is a very clear difference between these two. Right? So that we again use the principle of superposition to address this effect. So what we do, here we have this pumping well. What we do, exactly at the same distance, this is where the boundary is located. Exactly at the same distance, we add another well. It is called an imaginary well. If it is a recharge boundary like a wetland, river, this imaginary well should be a recharging well. Recharging well. This is a discharging well. This is a recharging well. Here we take the water out. Here we add water. That is how we do it. So that now you see, because of this, we have a cone of impression. Because of the pumping well, we have a cone of depression. So when it comes to this boundary, because the flow rate is the same, recharge and discharge rate are the same, this cone of impression and cone of depression should be equal at the boundary. So that this accumulative or the net drawdown becomes 0 at this boundary. So that it comes like this. But in other places, what happened? It become the summation or the net of the cone of depression and the cone of impression. That is why the drawdown become like this. Actual drawdown is this one. Sorry, the drawdown that we expect is this one, but the actual drawdown is this one. Right? That is when we have a recharge boundary. Same concept can be applied when we have a discharge boundary. Sorry, the impermeable boundary. Impermeable boundary is the boundary that blocks the water flow into the well. Right? Without this impermeable boundary, the drawdown that we expect is like this. But because it blocks the water flow from the right-hand side, this is not anymore now because it is an impermeable boundary. It blocks the water flow to the well. Actual drawdown is larger than what we expect. Right? So this is the actual one. This is what we expect. Again, what we do. Now suppose that this is where your boundary is located. Theoretically, what we do, same distance, we add imaginary well, image well. It is an hypothetical well. It is not an actual well. Because it is an impermeable boundary, we expect more drawdown. So in this case, both actual well and the imaginary well discharge water, take water out from the aquifer. Right? So that it becomes like this. So the summation of these two drawdowns will be equal to the actual drawdown. That is the logic. Right? So I need you to go through these examples and let me know if you have any questions. All right. So I think that's all what I can do for today. All right. So I will stop it now. But before I stop, do you have any questions to ask? No questions? Okay then. I will stop it now. And this is going to be the last class with you. So you can know more detail about your exam from Miss Hansani. All right. Yeah. Thank you very much.
Thank you, sir.